So we want to generalize the idea of determinant. To do this, we're going to introduce these things called cofactors. Essentially, they're the determinants of the submatrices times these signs, and the signs are generated in a checkerboard fashion. So if the index is 1 plus 1, which is the first element in the matrix, the sign is going to be positive, and then the next one's going to be negative, positive, negative, etc. And then in the second row, the first sign is negative, then positive, then negative, onwards, and then onwards and so forth. And this allows us to define the determinant in terms of any row and any column. Let me do a couple examples. So let's compute the determinant of this matrix. 1, 0, 0, 3, 0, 1, 0, 0, 0, 2, 1, 0, and 3, 0, 1, 0. And note this is the same determinant that we did earlier. But instead of using the first row, I'm going to use this formula, which allows me to use any column, and I'm going to use the fourth column. The reason I'm going to use the fourth column is because there's a lot of zeros in the fourth column. So the only thing I need to worry about when computing determinant using an arbitrary column is the signs. And this is where that checkerboard comes in. Our fourth column is going to start with a negative, then it's going to be positive, negative, positive. And so I can compute the determinant using these cofactors. Let's call this matrix A, for simplicity, as negative 3 times the sub determinant 0, 1, 0, 0, 2, 1, 3, 0, 1. And the sign in this determinant are called the cofactor. And then I get a bunch of zeros. So plus 0, minus 0, plus 0 times those subdeterminants. It doesn't matter what those are because they're all going to be 0. And now I have this one, and I can use an arbitrary row, arbitrary column. I'm going to use the first row, and I get plus minus, so it's going to be minus 1 times the submatrix formed by deleting that row and that column, which is 0, 1, 3, 1. And that's going to be negative 3, negative 1 times negative 3, which is negative 9. So we got the same answer as before, but we didn't have quite as many determinants to compute. Let's do another example. Let's compute the determinant of this triangular matrix. And we're going to do a general triangular matrix. Okay, so triangular means there's zeros in a triangle, and we have these zeros in the lower left, corner of this matrix. So we're going to use cofactor expansion along the first column. So this will be our first coefficient, and then we'll take the determinant of the submatrix formed by the remaining elements. You can already see the pattern emerging here. Then we get a bunch of zeros. And I guess the first 0 is going to be negative here technically, and then plus 0, minus 0, times those determinants. And then we get A11, use the first column again, so we get A22 times this little submatrix determinant. Plus 0 and 0. And then we see that we get A33 times A44. So this turns out to be a theorem. This is, in general, this is theorem 2 from chapter 3. It says the determinant of a triangular matrix is the product of the main diagonal. So just the product of these elements right here. Okay, let's do one more example. So if E is an elementary matrix, and we'll do the 3 by 3 elementary matrix, and it represents a row interchange what's the determinant of E? Okay, so there's really 3 of these in the 3 by 3 case. We could interchange the first row and the second row. We could interchange the first row and the third row. Or we could interchange the second row and the third row. And this is a mistake here. Okay, so these are our E's. Call this E1, E2, E3. And so let's now compute the determinant of this matrix. We'll use the first row. So this will be -1, because it's the second element of the first row, times 1, 0, 0, 1, which is -1. Determinant of E2, we'll use the first row again. That'll be +1 because it's the third element, times 0, 1, 1, 0, which is -1. Determinant of this submatrix is 0 minus 1, which is -1. And then the last determinant is 1 times 0, 1, 1, 0, which is -1. So it appears that the determinant of the elementary matrix representing a row interchange is -1. And this generalizes to 4 by 4, etc.